Thank you. Wow, I'm impressed. It's a real pleasure to present today at GYSS conference. My name is Paul Bruand. I'm a postdoctoral researcher at CNRS, which is a French laboratory hosted at the University of Tokyo in Japan. And my research is about DNA data storage. So let's start from the beginning. Throughout history, people have tried to keep knowledge safe, making sure it lasts over time and can be shared easily. So from ancient books to digital media like magnetic tape, floppy disk, SD cards, CDs, or whatever, we finally arrived at the era of the cloud. When you use that term cloud storage, it feels like data is floating in the air, but in reality, all of this information is stored somewhere. It's stored in massive data centers on the ground. Unfortunately, these data centers face significant drawbacks. They consume a large amount of energy, they occupy vast physical spaces, and they also lack durability. To illustrate the scale of the energy consumption of these data centers, let's take the example of Ireland. So in 2022, data centers accounted for around 18% of the total electricity consumption of Ireland. This is a huge ratio, and it's even surpassing urban dwellings. So this demand of electricity is constantly increasing as we generate and store more data. On this graph, you can see the growth and the future projection of global data creation. The units here are in zettabytes, so billions of terabytes. So we will probably reach 175 zettabytes by 2025, and we expect to reach more than 2,000 zettabytes by 2035, so in less than 10 years. So it's huge. This data doesn't only include like TikTok videos, like useless stuff. It also includes very important information like financial records, media archives, or also scientific data. For example, the French National Meteorological Service is now storing up to 2 petabytes, 2,000 terabytes per day of meteorological and climate data, which is really important for studying and combating climate change. So this brings us to DNA. So DNA is a polymer that already stores genetic information of living organisms. The idea behind using DNA as a storage medium is to encode digital data, so made of 0 and 1, into a DNA code made of ATCG bases. There are many advantages of using DNA as a storage medium. The two main advantages is that DNA is durable and dense. So it's durable because it can still be readable after thousands of years. And for density, you have to know that this is incredibly dense. To give you an idea, with less than 50 atoms, you can store like 1 bit of information. It's 1 million of times denser than current hard disk technology. And if we speak in mass, 1 gram of DNA could be equal to 450 exabytes, so like 4,000 data centers. So the DNA data storage process includes these steps that you can see on this figure. Just to show it briefly, you need to encode your information so from digital data into a DNA code. Then you have to write this information, that's the synthesis, and then you can store this information, find a way to store it in an efficient way. Then if you want to retrieve this information, you will need to read this sequence, so that's sequencing, and then to decode. So among these steps, the most important ones, if you want to make DNA as a data storage competitive, are synthesis and sequencing, writing and reading. Yeah, you can see it's like all technologies. It has to be cheap and it has to be fast. So here on this graph, you can see how prices evolved over time. So you can see that for sequencing, prices have dropped significantly due to technological revolutions that are second and third generation of sequencing. But for synthesis, prices have decreased, but there hasn't yet been a comparable breakthrough. The mainstream technique nowadays is called phosphoramidite chemistry, While it is very precise, it is actually too slow and too expensive for large data storage. So researchers are exploring other methods or improving methods. For example, they are trying to miniaturize the existing technique of phosphoramidite chemistry, but they also explore other strategies like enzymatic synthesis. The goal is to reach a fast synthesis of around 1 bit per second, so that would be 100 times faster than phosphoramidite chemistry technique. So as a conclusion, you've seen that data storage is vital for many fields, for archive, for scientific progress, but it is facing a critical growth, and there is like an energy consumption that is way too high. So DNA could be the ultimate data storage medium, but it needs a significant improvement in terms of cost of synthesis and speed of synthesis. Thank you.